So we've already looked at the idea of heat energy, and we've used it in some labs in order to quantify the amount of heat energy as Q being equivalent to the mass times the specific heat times the change in temperature. And we've looked at the idea of calorimetry and heat moving into and out of different substances. So, putting a hot piece of metal in water and allowing the water to heat up as a result of the heat energy moving from the metal to the water. So now we're going to talk a little bit about the different ways in which heat transfers, and then also we're going to talk about the movement of heat through the materials, as well as the idea that not only can gases expand when they are heated, but other substances that are solids or liquids can also undergo some amount of expansion or contraction based on the temperature. So there's three ways in which we can transfer heat. There's conduction, convection, and radiation. Convection is the movement of heat through a fluid. So really the fact that you have gases and liquids that can flow from one place to another will cause the heating up or the cooling of those gases to move heat energy through a system. So this has to do with like ocean currents or the movement of air in an air column. And it also can be like when you visualize water boiling on a hot plate, you can see these convection currents. We also learn about them in earth science when we're talking about the movement of tectonic plates on magma. So really the idea is that when fluids are heated, they become less dense and they tend to rise. So if you get a whole bunch of molecules moving at one time within a fluid, so a whole bunch of gas particles or a whole bunch of like water molecules, it causes what are called convection currents. And so we get these cycles where we have like cooling fluids sinking and then heating up and then rising. And so we get these currents or whatever in either vertically within the horizontal or within like a water column or a gas column. But also if we look at a map of ocean currents globally, we can see them moving like towards or away from the equator. Radiation, we're not going to go too much into it in this unit, but it will come back when we start talking about modern physics. So radiation is heat transfer from the sun, or really it's like a heat transfer by light particles or electromagnetic waves. And when we covered waves in the first semester of AP Physics, we talked about mechanical waves and transmitting energy as there were collisions between different materials. But in this case, radiation happens where we don't require any sort of interaction between matter. Electromagnetic waves actually can move through the vacuum of space, and they can transmit energy from things that are not matter, like photons, to things that are matter, like the atoms in metal. But again, this will come back later. What's more important for us to talk about now is the idea of conduction. So conduction is when you have molecular collisions between two different substances. So if I put a pan on a hot plate, there is going to be a transfer of kinetic energy from the surface of the hot plate into the metal of that pan, and then from the metal of that pan into the liquid in that pan. So these collisions that are happening between the adjacent materials are transferring energy, kinetic energy, from hot materials to colder materials. And so the high energy, faster moving particles will transfer energy to the larger ones. And that's how heat and temperature is essentially moving. So metals end up being pretty good conductors because of the properties of metals and the fact that metals tend to be this like sea of electrons where electrons can move and we can create these chain reactions between adjacent molecules, or atoms of the metal. So metals are said to be good conductors of both heat, but also of electricity, which will come into play in the next unit. So if we wanted to quantify the rate of conduction or the rate of heat movement, remember whenever we say the rate of something, we would say, like that over time. So in this case, we're talking about energy, heat energy, or Q over T, the amount of time. We can quantify that based on several different variables, and it really makes sense. I'm going to actually kind of skip past this and go to the next slide, and then we'll come back and look at the equation. So to me, I always think of thermal conductivity as being in terms of a window. So if I were to think about, how would I design a window, or how does heat energy move into and out of a building through windows? And it allows me to sort of figure out what the equation is without memorizing it. So if we look at a window, the windows have some amount of cross-sectional area. So the larger the window is and the larger the surface area of the window is, the more likely you're going to lose heat across that window. Another thing is you're going to lose more heat the colder it is outside, right? So if there is a big temperature difference between what's inside and outside, that's going to increase the rate at which heat is lost. The other thing is the thickness of the window. So if you have a really thick window, it's going to take a lot longer for the heat to transfer out of the building than if you have a very thin window. And then also whatever the material of the window is made up of is going to affect it. So some materials will transmit or conduct heat at a different rate than others. So if we actually look at the equation, it sort of makes sense. The rate of heat transfer is directly proportional to the thermal conductivity constant. So that's K. That's about a property of the material. A, the cross-sectional area. So the bigger the area, the faster the rate. And then the change in temperature, so the difference in the temperature outside or from one side to another would increase. So the greater that difference is, the greater the rate is. And then it's inversely proportional to the length. So the longer it is, so the bottom of the fraction, this is actually an L here, the longer it is, the heat has to be conducted from one place to another. It's going to actually increase the time. All right, so if we think about ways in which heat is moving, we also have to think oppositely about heat not moving. So that's the term of insulation, where we can develop materials that will reduce or don't transmit heat very well and can prevent the movement of heat loss from one place to another. So keep in mind that we will talk about insulators and things that are thermally insulated as we get into thermodynamics. So the last thing I want to talk about in this video is about thermal expansion. So we know, we just went through all of these gas laws, where if we increase the temperature of something, it's going to increase the volume. And this is for gases. Does this also apply to solids or liquids? And the answer is yes. So as we heat, these materials expand. As we cool, they can contract. Water is sort of the odd man out here. Water does become more and more dense and therefore sinks as it becomes cooler, up to about 4 degrees Celsius. But once it starts to freeze, it forms into this sort of honeycomb shape, and it actually, in this like crystal structure, and it actually becomes less dense. And that's why ice floats on top of liquid water. Whereas any other material, if it was the solid form would be more dense than the liquid form, and it would actually sink. The opening of a tight metal lid. So a lot of times, like if you go to open like a pickle jar or something and you can't get the top off, one way that you can try to loosen the lid is to run it under hot water. And by doing that, the metal expands and it allows the lid to sort of loosen away from the glass. So there's a way that we can quantify this rate of expansion, and that is using this equation. So we have either the linear expansion or volumetric expansion. So this just says that the final length L must be equivalent to the initial length times 1 plus alpha change in T, where alpha is the coefficient of linear expansion, and that is a given or known value for different materials. So like brass or steel or copper have a different coefficient of linear expansion. If we're going to look at it volumetrically, it's the same thing, except our constant's just a little bit different. So the final volume is going to be equivalent to the initial volume times 1 plus beta change in T, where beta is the coefficient of volumetric expansion, and again, just applies to different types of materials have a different coefficient of expansion. So in class, we're actually going to look at some examples of both thermal conductivity and some demonstrations on thermal expansion so you get a little bit better idea of it.